Good morning, hope you're doing well. I'm Ben Cohn. Today we're going to talk about the quotient rule and square roots, tangent of x, and then we'll get a little bit into the idea of implicit differentiation. So far we've gone over the power rule, the product rule, and the chain rule. And that's pretty much all you really need in life. Well, I guess, and the definition of the derivative. Okay, so I mentioned it before, I have a great disdain for the quotient rule. The idea of the quotient rule is that there is, if you have something along the lines of, let's say, adjust, f of x equals u over v, okay, then there's some way of finding that f prime of x equals something. And I just don't do that. So I'm going to rewrite this slightly, just so that my notation doesn't overlap too much. Instead of u and v, I'm going to use m and n. Whoop. I know they're normally used for integers, but that's okay. We'll get past this. This will be m of x and n of x. So the idea here then is I'm going to take this and I'm going to rewrite it so that I don't use the quotient rule at all. I'm just going to go straight product rule. So the idea here, we have m n to the negative 1. And so here we say, okay, we're going to use the product rule here because we have m times n. But then when we find the derivative of n, we're going to have to use the chain rule because we have a nested function. So if we approach this from the product and chain rule kind of idea, then we have the product rule, which is u v prime. That will give us uv prime plus u prime v. So we'd say, well, u here is m, v here is n to the negative 1. U prime would be, let's say, m prime. And then for v prime, we would do the chain rule. So we take this, the negative 1, move it down like the power rule. So we do negative 1, n to the negative second. And then we multiply by the derivative of n, which is just, we'll call in this case n prime. And then when we put this all back together, so we have, change colors, blue. I do enjoy blue. So from up here, we have u would be m times v prime, which is n prime all over n to the negative second. Yes, n squared. And then it'll be a negative. Then we'll add to that the m prime, yes, over n. And it looks like we're going to want to combine these, so we'll multiply by n over n. Two things you can always do in math. You can always multiply by 1, and you can always add 0. So multiplying by n over n is the same as multiplying by 1. So rearranging things slightly, we got m prime n all over n squared minus m n prime all over n squared. Then we can combine those. And so let's see, u correlates to m. I'm going to rewrite this in a more standard u and v notation. I just wanted to avoid the u and v earlier because that way you don't have like u equal, it would have been crazy. Okay, so let's see here. M prime is the same as u prime, and n is the same as, similar to v, minus, let's see, I totally lost it, I had it. So wait a sec, u is associated with m, so this would be uv prime all over v squared. Okay, got it. So our back to blue. If you have the u over v, then that would be the same as u prime v minus u v prime all over v squared. And so this is what the quotient rule is. The idea with the quotient rule is if you have a quotient, it kind of does the product chain rule for you already. And it'll always turn out the same. The reason I ignore it is because for me, it's easier to write out whatever equation we have in terms of the product rule, where one of the products is to the -1, and then just do the chain rule, than it is to actually remember what the quotient rule is. Because one of the human performance traps you have here is you have a negative sign, so it means that you have to memorize the actual order of which u prime, which v is there. And then you have to have a v squared in the bottom, so it's like you have to kind of remember which one, the u or the v, has to be squared and put in the bottom. And when you're trying to memorize it, it's just a bigger human performance trap than it's normally worth. So I don't remember it. I just do the product rule every single time. Show you an example. So with the example, we're actually going to go straight over to tangent of x. So now that we have the concept of how to do quotient, we have, let's see here, tangent of x, tangent of x, tangent of x, f of x equals tangent of x. And tangent of x is just equal to sine of x over cosine of x, which we can rewrite as sine of x cosine of x to the -1. So now we have our u and v set up here. Light blue, light blue. I enjoy light blue. Whoop. So we'll say u equals sine of x, v equals cosine of x to the -1. We know that u prime then becomes cosine of x with so positive sign, the derivative of positive sign is positive cosine of x. And just as a reference point, I'll write up the product rule right here, uv prime plus u prime v. So now comes the challenging part. All right, we need to find the derivative of secant of x, which is 1 over cosine of x. So this is going to be the chain rule. So the chain rule is f of g of x prime equals f prime of g of x, probably another parentheses there, times g prime of x. So f of x in this case is x to the -1, because we say x is the center part, which this is the outer nesting function. And then, therefore, g of x will be cosine of x. Whoop, whoop. Cosine of x. Okay? And so from here, then, f prime of x equals -1 x to the -2. Let's see, -1 x to the -2. Okay? Which I will rewrite as -1 over x squared. G of x will then be negative sine of x. So the way I remember that is derivative of sine of x is cosine of x, and then the derivative of cosine of x is sine of x, except the sign will be reversed, the opposite. So we have negative sine of x. Okay, so now when we put that all together, so f prime of g of x, so negative, let's see, negative cosine of x all over, no. Whoop, whoop. So f prime of x is -1 over x squared. And then instead of x, we put cosine of x. So cosine squared of x, -1 over cosine squared of x, times g prime of x, which is right here, forgot the prime, negative sine of x, and then we take the double negative, make it a positive. It's always good to be a little bit positive in life. Then we have cosine squared of x. I know it seems like a lot of work. It's a reasonable amount of work, but we got a reasonable enough answer. So now we have v prime equals sine of x over cosine squared of x. Okay. And you could have done that using the, well, no, we're still moving on. Okay. Okay. Now we go put everything together. We just use the chain rule to find that. I know it felt kind of complicated. You actually get to the point where you can do the chain rule in your head pretty well. So like if I was doing it the way I would visualize this mentally, do some red. The way I'd visualize this mentally, I'd be like, all right, take the 1, you move it down, -1, times, and then the middle part stays the same. Wait a second. To the negative, and then you have the -2nd, because you brought the -1 down for the power rule. And then we would multiply by the derivative of the interior, so it'd be sine of x, negative, because it's cosine, positive, and then we'd simplify that to the same answer we had. So it's actually fairly reasonable to be able to do the chain rule mentally without writing it down. I wrote it out that time just to be more explicit. Product rule I like to write out, but for the chain rule I usually just do it mentally. Okay, and with practice you can as well. So we have, for the final answer, we have u sine of x times sine of x all over cosine squared of x plus u prime, which is cosine of x, all over cosine of x to the -1. Yes. Yes, I think so. Oh, okay. So the -1 will go away. Yes. Yep. Confident. So u prime cosine of x times cosine of x to -1 cosine of x. Okay. So we're left with this. So we're like, what do we do at this point? Well, again, we're going to try and multiply by 1. You'll see this kind of as a common theme when you're doing the product rule in place of the quotient rule. Multiply by 1, cosine of x, cosine of x, and we are left with sine squared of x plus cosine squared of x all over cosine squared of x, which equals, we know that sine squared plus cosine squared is 1. That's the Pythagorean theorem. I don't know. Pythagorean. And the 1 over cosine of x is secant of x. Therefore, after all this massive amount of work, we can tell that when f of x equals tangent of x, f prime of x equals secant squared of x. Now your next question is like, wow, that was a lot of work. Should I just memorize that? Yes, you should. I'm usually against memorizing things in general, but tangent of x comes up enough, and you're expected to know. You're expected to know a lot of things that like I don't bother knowing. Like for example, the quotient rule. It's like the AP test assumes that you know it. Don't know it. Just derive it every time. Or treat it the way I did, where you rewrite sine of x over cosine of x as sine of x times cosine of x to the -1. And by working that out, I think it's a lot safer than trying to memorize the quotient rule and then getting it wrong. Granted, you don't have to be perfect on the AP test. I think you only need like a 60% probably to get a 5. So 60% is still perfect, which is like, well, okay, that seems reasonable. Doesn't mean you should be throwing away a point. It's still pretty darn hard. And so the question then is, should you memorize tangent of x? And I think you should. It comes up often enough that you want to be able to quickly get it. And it's unique enough that, memorize it. It's just worth your time. It's a good investment to install those penguins on the iceberg. Just move them in, build the house. I guess probably igloo. Penguins probably don't live in igloos. Just learn it, memorize it, take a piece of paper, write it down about 50 times, and then it'll be burned into your soul. Okay, so now that we know the idea of tangent of x, which you should memorize, and we also showed how you can use the product rule and the chain rule together in place of the quotient rule, which I think is a good technique. We're going to move on to square roots. Now you probably guessed already how to do square roots. Maybe not. They're not hard. You just use the power rule. But it's good to show you just so that it doesn't catch you unawares. So if you have, let's say, f of x equals 3x to the 1/2, you look at this as, okay, the 3 is a constant, so we kind of pull that out. X to the 1/2, well, that's just a power, so we'll take the 1/2, move it down here, and then we'll subtract 1 from the top part right there. So we go 1/2 minus 1 is negative 1/2. So f prime of x would be 3/2 times 1 over square root of x. And that's all there is to square roots. Square roots, you just rewrite it as a power, as a fraction power exponent, and you take that fractional exponent and then you just apply the power rule to it. Then you do get things that you don't quite expect, like 1/2 minus 1 is negative 1/2. So it basically moves the x down to the denominator from the numerator, but that's okay, not a big deal. It's something you can live with, something you can go with. So that's the way that square roots are approached. Not hard, but if you've never seen that before, then it gets kind of confusing and intimidating. You're like, well, is this an exception? It's like, nope. Use the exact same thing as a power rule. You just play it to the hilt. Okay. Now, off to something conceptually a little bit different and some new ideas here. So, there's a concept called implicit differentiation. So we're only going to do this with ordinary differential equations. So calculus will kind of branch off into two branches. You have ODEs and PDEs. PDEs are partial differential equations. ODEs are ordinary differential equations. And pretty much the definition is ordinary differential equations have one independent variable. And partial differential equations will have one or more. But traditionally, it's almost always going to be more. Multiple independent variables. And I know at least when I got to calculus, I really did not have a good grasp of what an independent or dependent variable was or what it really meant. So I'm going to explain that real quick. So when you have a graph, you might be like, well, how many dimensions is this graph? So we have a graph here like this. I can do better. That y-axis is just not sufficiently vertical. So we have an x-axis, we have a y-axis, and we have some sort of graph. It looks kind of like this. And you're like, oh, well, this is a two-dimensional graph. And when you say dimensions, there's not really a good one set. This is what the definition of a dimension is in mathematics, which is kind of bothersome. Well, there's lots of definitions of it, but there's no one set definition, and depending on what you look at, it kind of means different things. What I mean by that is degrees of freedom. So the idea is this is one-dimensional, partly because it's a line, but the idea is you put it in x and you get out some value y. This y value is f of x. It's really just a function of x. There's only one value you can put in. You can put in your x value. Well, what would two-dimensional look like then? So a two-dimensional graph equation system might look something like this, where you have an x-axis here, a y-axis here, and a z-axis here. And you put in some combination of x's and y's, like so, and that gives you a value, z, where this z value is a function of x and y. You can put in an x and a y into this. And so you get some sort of plane or curve. The z-axis, your f of x, y, can be measured in area. It can be measured in x's times y's, whatever the units of x's and units of y's are, multiplied by each other. So you'll get an area. Now, your first thought process is like, okay, so xy, one dimension, xyz, two dimensions. Not necessarily, because you can have an xyz coordinate that's only one dimensional as well. The idea here then would be you have something like this, something like that, something like, nope, more vertical. There we go, but then I missed it. I'll move it over. Huzzah. So the idea here is we have our x, y, and z here. But in this case, the z is just going to look like a line, some sort of line. And one of the ways you can get this sort of situation is you put in an x value, that creates an y value, so you have y of x, y of x, and that gives you your z value. So you could be like, well, this z is of x and y, but really, since y is a function of x as well, you have z of x, y of x, which is the same thing as z of two values of x. And so what you get then here would just be a line. It'd be a line in 3 dimensions, as far as 3 coordinate plane dimensions, but you could, and I consider this to be a one-dimensional graph, because it's just a line, and it would be measured in just like meters. It would be measured in a length, so to speak, not an area. And so that's what I mean by an independent variable. So here it would be one independent variable because you have one input. Here it'd be two dimensions because you'd have two independent variables. You can put two variables in that are independent of each other. And then you get back to your standard two-dimensional plot, you have one dimension. So looking at this from a more, I guess, conceptual, story-based Aesop fable sort of perspective, let's say you are on the side of a cliff, and you have a gear like this. And I guess I should draw you just to be safe. And there's some sort of pulley system and a block. And the idea here is you turn this block here, or turn this pulley, and the block is going to go up. You only have one. This will be like your x input. You put in how fast you turn it. That has to do with how fast the block comes up or down in the position of the block. Well, let's change this a little bit then. So now we have two wheels, two gears, two things with hands that look like angry eyes, but they're not. Now it looks like angry eyes that are crying. That's not the point. Whoop. So these are connected through some sort of meshing of gears. Whoop. And there's some sort of rope attached to it, and then it goes to the block. Okay. So now the idea here is, I'm going to call this one X and this one Y. You can turn the X wheel gear, or you can turn the Y gear, but the thing is they affect each other. So they are not independent because these gears are meshed together. Not mashed, meshed. Meshed together with an E versus an A. And so you can't turn one without the other one turning in relation to it. Now they might have a different gearing ratio. So like this one might be easier to turn but provide less motion of the block. But just because one's easier or harder to turn than the other one doesn't mean they're independent. You might have a high-speed low torque and a low torque high-speed pinion, gear, etc. gearing. But they're not independent of each other. You can't turn one without the other without the teeth breaking. And so they're not independent. And so this would be an example of one degree of freedom or a one-dimensional system because X and Y depend on each other. Moving on, if you have, again, let's say two boxes or wheels or pulleys or some such, and this one attaches to the block again. We'll call this one x, call this one y. This one also then attaches to the block too, but attaches in a funny sideways motion so that the x will move it up or down, but the y will maybe, let's say, rotate it. So you can rotate the block, or you can move the block up and down. This would be two independent inputs, because you can adjust x however you'd like, and you can adjust y however you like. They're not connected to each other, and the result will be a two-dimensional system where you have a block that's moving both up and down, but also rotating. And so that's what we mean by one independent variable or two independent variable. Everything we're going to deal with will be ordinary differential equations and one independent variable. It's a sort of thing where it is so exclusively ordinary differential equations in Calculus 1 and 2, like the first 2 semesters of calculus or for the AP exam, that for the most part you don't even understand that there's ODEs and there are PDEs, because it's just so blanket statement ordinary differential equations that you don't really understand some of the other nuance that's out there that you're kind of tiptoeing around with a lot of your problems. And so it is good to understand that for the most part we're only going to have one independent variable. And this brings us to a point on notation. You'll see that a lot of times when I want to take the derivative of something, I'll be like, well, d dx will also be a derivative with respect to x. Or sometimes I'll do d dx like this with a small delta. Is that small delta? It's a different type of delta. I should look up what kind of delta that is. Not important. So the idea then is, this is traditionally, the second one is traditionally a partial differential equation. This is a complete derivative. So a partial derivative is not exclusively, but almost always associated with PDEs and not ODEs. But if you use a partial derivative in a ODE, basically use a partial derivative when there's only one independent variable, then they act exactly the same. They're interchangeable. They are the same thing. The concept of a partial derivative is if you have, let's say, 3 independent variables. You have f of x, y, and z, and that equals 3x plus 2xy plus 3yz. And you want to take the derivative of this with respect to x, then what you do is you hold all the other variables constant. That y, it's basically the same as if it was like a 3. So the answer for this would then be derivative of 3x with respect to x would be 3 plus 2xy would just be 2y. And then the derivative of 3yz, well, those are all considered constants, so that would just be 0. You could also then take the derivative with respect to y. You could take the partial derivative with respect to z. And this will tell you different things based on what kind of physical phenomena you're trying to model here. And that's what partial derivatives are. But if everything you have is just a function of x, f of x, and you have something like 3x, do 3x plus 2xy, where y is a function of x, let's say y of x equals 3x, well, you really only have one variable that you're dealing with here. That y, for all intents and purposes, doesn't exist. You could just think, okay, that's some grouping of x. So you could solve it using the chain rule and finding the derivative of y, 3x plus 2x times 3x, or you could just substitute in 3x. So this here is the sort of thing we're going to deal with. Multiple independent variables we will not deal with. But when you see this partial differential equation, it's normally talking about multiple independent variables. But if we talk about a partial differential equation in terms of a single independent variable, it's exactly the same as the derivative you're used to. So when you say take the derivative of, and you're talking about an ordinary differential equation with one independent variable, that's the kind of derivative we're thinking of. it really becomes difficult when you have something with multiple independent variables like f, x, and y, and z, and you're like, all right, take the derivative of that. It actually becomes fairly ambiguous. It's like there's not really a good definition of what is the derivative of a function with multiple independent variables. There are different things which all kind of count under the subcategory of the derivative, but a lot of it's going to come down to which physical phenomenon you're trying to model. So we're not going to worry about that for now. I'm just saying that there's a bigger world out there, and be careful when you have multiple independent variables in your function. A lot of things that are hard and fast and you know as facts in life aren't really as much true. Now, when you get down to the basic definition of a derivative in terms of small change in x, small change in y, then a lot of that actually applies. But it's challenging. Yeah, it's a challenge to kind of go through and re-look at everything. Okay. So one other quick tangent into independent-dependent variables. So you have, like up here, you have your x and y. You have your function. And you have your x-axis, you have your y-axis. And it's like, well, how do you know which one's the dependent variable and which one's the independent variable? Independent is what you put in. What you get out is the dependent. So for us, conventionally, you'll almost always have either x or t or something along those lines be your independent variable, which you put in. What you'll get out will be your f of x or your y. Well, that's not always, you can do that, but you can always usually look at these functions and then just reverse it around and be like, well, no, I want the y to be the independent variable. I'll put it in a y, and what do I get out for x? As long as you have one input, one output, or if you have one input, then that's going to be your independent variable. And whatever your input is will be your independent variable. So for example, if we go back to our wheel, pulley, and gear situation, traditionally you'd be like, okay, I want to pull this, I want to change this gear here and rotate this gear to lift the block. That just kind of seems convenient, kind of the common sense sort of thing. Well, you could also imagine if you take the block and you pull on that, then that would affect the gear too. But very rarely are like, I want to spin that wheel, so I'm going to pull this block. It's just not common. Totally would work. Totally acceptable. It's just unusual to use a machine like that in that direction. Same thing with graphs. It's unusual to draw a graph like this and be like, okay, I'm going to put in y and expect an x out. Totally works, totally fine. It's just not the way that it's commonly done. And so if you see something where that's going on, it's not necessarily wrong, but your spider senses should be kind of kicking off. Okay, so now with all that in mind, what's an implicit differentiation? So sometimes you can't solve for y explicitly. Like when you say solve for y explicitly, it's like where you have y equals 3x plus 2x squared minus, you get the idea. I probably should finish that up. Square root of 3. You can't always solve for this. And so sometimes when you have y is kind of jumbled up in there, you can still find out what the derivative is. Usually, often, pretty much always. Usually. So for our example, we're going to say that we have y squared minus 9x squared equals 0. And you could be like, oh, okay, well, we'll rearrange it and solve it for y, and then we'll do the normal derivative stuff that we always do. And they totally can. And that's why I chose this example. It's because you can do it both ways. And it'll help show us the idea of what's going on here. I know, I'm just trying to decide on which color. I'm going to go with purple. I know, I always go with purple. I like purple. And crystal light. Okay. So the idea with implicit differentiation is we'll take the derivative of the left side, take the derivative of the right side. Basically, you can do anything in math as long as you do the same thing to both sides of the equal sign. So I'm gonna rewrite this a little bit as y of x, so it's very explicitly, obvious, unambiguously, a function of x equals 0. And so we're going to take the derivative of y of x squared. So to do that, we'll do the chain rule, because you have some sort of nested function here. This nested function is y of x. And so we'd have 2 times, I'm going to write it now back as y without that x there. I know, it becomes kind of confusing, because like, wait a sec, does that mean it's a function of x? Does that mean we're multiplying by x? What's those parentheses? I know, I'm sorry. And I keep moving back and forth between these notations, and that's why I try and say out loud what's going on. But just looking at this, you're like, wow, that's darn confusing. A little bit sometimes. Okay. So we bring the 2 down, 2 times y to the first, times the derivative of the interior. The derivative of y with respect to x is the derivative of y with respect to x, just like this, minus 9 times 2 times x to the first. And then you can also do, this is to the first. I know, sometimes I use that as prime as well. It gets confusing. I'll zoom in more and make that a explicit one. There we go. Does that make it better? I don't think it makes it better. It makes it better, but not good. Okay. And then if we wanted to do, we could be like, well, we'll multiply the derivative of the interior 2, which is derivative of x with respect to x. I like to do that when I do implicit differentiation. It just helps me make sure I don't miss steps. And it's like, well, okay, that's obviously just 1. Derivative of x with respect to x is 1. And you can kind of look at this as derivative with respect to x of x to the first, and then do the product rule and get 0. Or you can look at it as, oh, derivative of x on top, dx on bottom. The same thing on top and bottom means it's going to be 1. Not always true, because you can have 0 and 0, or you can have infinity, infinity. But as long as we have a determinant form, we're good here. So we're left with this, and then we take the derivative of 0, and that equals 0. Rewrite things a little bit. We have 2y dy dx equals, move this over to the other side, we have 18x, and then that leaves us with dy dx, the derivative of y with respect to x, equals 18x all over 2y. These cancel and gives us 9. And we're like, oh, okay. So our answer is 9x over y. That's not really all that useful. Sometimes it is. Sometimes it's not. Because if you were given like an x and y coordinate, you'd be like, okay, this is the x, that's the y. Solved. So now what we're going to do, I know this is kind of sort of almost feels like cheating. You'll get over it. Orange. I know I don't use orange. It's just too bright for me. I don't know. That's okay. I'll use it this time, though, so it doesn't feel left out. So we have y squared equals 9x squared. And therefore, we can take the square root of both sides. And without trying to worry about the whole negatives, we'll say absolute values here. So we have y equals 3x. And so we come back down here, and we get 9x divided by 3x, which then just gives us 3. So dy dx, the derivative of y with respect to x, of this equation is 3. You're like, oh, okay. And the reason I use dy dx for this sort of situation as opposed to f prime of x, because we really aren't given a function of x. A lot of times f of x and y are interchangeable, and we probably could, but in this case it's easier to say find, so you have a question like this, be like find dy dx. Okay. And so, think. Okay. So now we're going to rearrange this and do this a different way. So we're going to go straight for the explicit solution without using implicit differentiation. So then we'd go like we did last time, y squared equals 9x squared, which gives us y equals 3x. Take the derivative of both sides, and we find that, oh, dy dx equals 3. And you can kind of look at what we're doing right here as implicit differentiation. So here we did implicit differentiation, we got a y. This, we did implicit differentiation, but we made sure that we had y all by itself first. And then when we do implicit differentiation on y alone, well, we have y to the first. That becomes, by the power rule, 1 times y to the 0, which equals 1. And then, as part of the chain rule then, when we do this, we multiply by the derivative interior, which is dy dx. So really, we're always doing implicit differentiation. It's just that when we solve for y explicitly first, i.e. we get a little y over by itself, then our implicit differentiation always comes out to dy dx. And so previously, and a lot of times, you just ignore that what you're actually doing is implicit differentiation. And so this is what's actually going on. So you have your, you take your derivative of y with respect to x, and you get dy dx. That's the idea behind implicit differentiation. Now, let's go on to another example. This is, you won't see an example like this, because if you encounter something like this in the wild, your thought's just, oh, let's just solve for y. Solve for y, take the derivative, bam, go home early, no big deal. And that's why you won't see this sort of problem for implicit differentiation. So you'll see something more along the lines of, let's say y to the fifth minus y equals x. And you really can't solve this, and then we'll be like, well, find dy dx. Find dy dx. And you really can't solve this for just x, for y on its own. You might think that, yeah, you really can't, because it's like, well, let's factor out a y, you get y to the fourth minus 1, but then it's like, well, that's difference of squares, so then we have y squared plus 1, y squared minus 1. It's like, oh, okay, now we got a y plus 1 again, another y minus 1. Maybe we can do this. And then you just get bogged down in all this algebra, and it's going nowhere fast. So what we do is we just ignore that algebra, which is going to bog us down and make our life more difficult. Muddy, muddy algebra. And we go straight for implicit differentiation. So for here then, we'd be like, okay, implicit differentiation, we have power rule, 5y to the fourth times dy dx. So that's the chain rule. So we take the 5 down, y to the fourth, that's the power rule, multiplied by the derivative of the interior nested function, which in this case is y. And that gives us dy dx minus derivative of y to the first here, so it would be 1 y to the 0 times derivative interior dy dx. Y to the 0 is 1, 1 is 1, we're left with just dy dx. And then we take the derivative of x with respect to x, which will be 1. Rewriting this slightly, whoop, 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 whoop. Red, purple, you're right, green. Okay. Factor out dy dx. We have 5y to the fourth minus 1 equals 1. And then we say that, okay, dy dx equals 1 over 5y to the fourth minus 1. And then you'd be like, what? We can't have y over there. That's part of, dy dx, part of what? What? Can we do that? It's like, yes, we can. We can have the derivative of y with respect to x as a function of y. Totally fine. You'll see it a lot. Before, when we had our previous example, we could solve for y and then plug it back in. Sometimes you can do that. Sometimes you want to do that. Sometimes you don't. And so it all depends on which situation, how you want to use this. So if this question is find dy dx, then it's like, okay, bam, dy dx. Now on the AP exam, a lot of these things will come up probably like on, you won't see much of this on the AP exam, but when you do, it'd be the sort of thing where then you'd have a multiple choice about like which of these solutions is a solution to dy dx. And then you'd be like, well, okay. So you'd find your solution, something like this, and you'd try and match it with one of the possible solutions. It might be the sort of thing where none of the possible solutions exist, but it matches the one that you found, and you might have still done everything correctly as well. It could be just got the wrong answer, but we're not going to go with that. So it might be a situation where you have to basically rearrange your solution to match one of the solutions that's available. And that'd be the sort of thing that you'll see with implicit differentiation. And so that is the idea with implicit differentiation. So to sum up what we did here, we covered some of the concepts you guys already knew how to do, but you weren't really told unambiguously, without confusion, how to do it. So like we talked about the quotient rule, which is really just the product rule and the chain rule put together. I talked about square roots, just the power rule, but now you're dealing with fractions of a power instead of whole number integers. And then we talked about tangent of x, which was an example. Actually, out of order. It's okay. We talked about tangent of x as an example of the quotient rule, and the derivative of tangent of x equals secant squared of x, which is something you should memorize because it'll come in handy many, many times, especially when you start getting into integrals. You should be able to see secant squared of x and be like, oh, that's tangent of x. And then we talked about implicit differentiation. Implicit differentiation is something that we always do, but sometimes it's disguised because we solve the equation for y first and then take the derivative. When we talk about implicit differentiation, we're only really talking about one independent variable here. And we talked about what independent variable means. One independent variable here really means you just have one input and you get an output. So that is all for this class. We will see you next time. Wish you best luck. Thanks for stopping by.